In this video, I'm going to solve this optimization problem. So I want to make an aquarium. It's to be made 6 feet high, and it's to have a volume. So let's label that 6. It's to have a volume that is 750 cubic feet. So let's label this X, and let's label that side Y. So the base ends and back are going to be made of slate. The front is going to be made of plate glass, which costs a bit more than slate. And we want to choose the dimensions to make the cost of raw materials a minimum. So first of all, I am given that the volume 6xy is 750, and I want to minimize the cost of the materials. So let's first of all think about the surface area. So the base, back, and ends are all going to be made of slate, which all cost the same thing. So let's go through those ones. So the area of the back, okay, so that is going to be 6x. And the area of the two sides, so by the two sides, I mean this one and this one. So those each have area 6y. So that's going to be 2 times 6y, or 12y. And then the area of the bottom is going to be xy. So the bottom has area xy. And then we have the front, which has area 6x. Now I'm going to want a cost function, and I'm going to want it to be in terms of one variable. And right now I have two variables around here. I have x and I have y. But I know that 6xy is 750. So that tells me that actually y is 750 over 6x, which simplifies to 125 over x. So that tells me I could rewrite the area of the two sides as 12 times 125 over x. And I could write the area of the bottom as x times 125 over x, which is actually just 125. And now keeping in mind that the cost of the back, the sides, and the bottom are all the same. So let's let A be the cost of the back, sides, and bottom per square foot. Then we're given that 3/2 A is the cost of the front per square foot. And now we can get a nice formula for the cost per square foot in terms of x. So I've gone ahead and written that out. So the cost will be the cost of the back, sides, and bottom per square foot times the amount of material needed for those portions, plus 3/2 A, which is the cost of the square of the front per square foot, multiplied by the amount of material needed for the front. And let's simplify that a bit. So I've gone ahead and expanded and simplified to get this. And I've listed x as being in the interval 0 to infinity. And now I'd like to get the critical numbers. So to get the critical numbers, of course, we need the derivative. So let's go ahead and differentiate. Now keep in mind that a is just a constant. So when I differentiate, I'm going to get a multiplied by the derivative of this, which is going to be 15 minus 1500 over x squared. And I want to know when that's equal to 0, so I'm going to rewrite it as 15x squared minus 1500 over x squared. And so c prime of x will be 0 when the numerator is 0. And so that's going to happen when 15x squared minus 1500 is 0, or when x squared is equal to 100. And technically there are two solutions to that. X equals plus or minus 10, but of course the only relevant critical number here is x equals 10. So I'm going to deal with x equals 10. That's my relevant critical number. And I'd like to show that that indeed gives me a minimum, and I'm going to use the first derivative test this time. So I've gone ahead and given a sign diagram for the derivative. So keeping in mind this is my derivative here, and a is certainly positive, and so you can see that it's decreasing and then increasing. So by the first derivative test, x equals 10 gives a minimum. So I've gone ahead and recorded that, and recalling that y was 125 over x, that means that y is going to be 125 over 10, or 12.5, and we were given in the beginning that the height was 6. So putting that all together, the dimensions that minimize the cost are 10 by 12.5 by 6 feet.